scope of the effort is hard to capture in words or even pictures. The challenge was clear. Correct a steam path erosion problem at the Vermont Yankee nuclear power station. Do it right. Do it safely. Do it economically. And do it in 6 weeks. There was no precedent, no tested process, and no experience base. Interact, innovate, question all barriers, take ownership, and do it. We hope this video will give you some idea how a seemingly impossible task became a great success, how the challenge was met at Vermont Yankee and for other plants of a similar design. Vermont Yankee is a 540 megawatt boiling water reactor located in southern Vermont. Since beginning commercial operation in November 1972, this nuclear generating station has been a consistent top performer among domestic BWR plants, with a lifetime capacity factor greater than 75%. During a routine maintenance overhaul in 1989, the staff at Vermont Yankee discovered severe erosion-corrosion of the low-pressure turbine internal steam path components. There was extensive structural and efficiency damage. Steam turning vanes, diaphragms, sealing ledges, axial support ribs, extraction boxes, welds, and casing wrapper plates were all being attacked and eroded, in some critical areas to as much as 1/2 the original thickness. Extensive discussions with other utilities and manufacturers traced the root cause of this erosion corrosion to the incompatibility of the original low-alloy carbon steel with the wet steam environment inherent in a non-reheat turbine cycle design. The damage was found to be non-uniform, progressive, and irreversible. It was a function of service life, and if allowed to continue, would compromise performance, weld integrity, and structural strength. Ultimately, it would introduce unacceptably high maintenance costs and failure risk. Ironically, because of its very successful operating history, Vermont Yankee became the first of its class to suffer erosion-corrosion damage to this extent. Potential solutions were examined with the assistance of sponsor companies, other utilities, and OEM turbine suppliers. Weld overlay, cladding, flame spray, component replacement, reheat, or complete replacement were all considered. The recommendation was made to the Vermont Yankee Board of Directors in January 1993. Complete replacement of all steam path components of both low-pressure turbines in a single 6-week refueling outage, an option never before attempted in the industry. Total steam path replacement using improved construction materials would provide an undeniable solution to the erosion-corrosion problem, and through cycle isolation and design improvements would increase performance by 3% at a cost per kilowatt hour less than the current bus bar cost. However, in an environment of increased competition, downsizing, and cost reduction, any recommendation involving a substantial expenditure had to survive rigorous financial analysis. Clearly, financial analysis and the board's decision would determine the future of Vermont Yankee. The analysis included the impact of each alternative on O&M cost, capital investment, efficiency, reliability, depreciation, interest expense, taxes, and sponsor company avoided power cost. These factors were modeled over the remaining licensed life of the plant to determine the overall cost in nominal and net present value terms. The primary decision variables were incremental cost per kilowatt hour, total net present value revenue requirements, total avoided cost, and net NPV power cost impact. The financial analysis concluded that replacement provided the lowest cost by a margin of 2-to-1. Turbine replacement using improved construction materials would not only solve the erosion-corrosion problem, but would result in a 3% performance improvement through system performance and turbine design improvements. Cost per kilowatt hour would be less than the current bus bar cost. At the same time, all identified turbine operational problems, such as torsional vibration and stress corrosion cracking of blades and wheels, would be resolved. O&M inspection and testing costs would also decrease. The Board of Directors approved the $33 million project in February 1993, and on March 5th, General Electric Company was selected from a field of 4 well-qualified international bidders to provide 2 new, fully bucketed monoblock rotors with state-of-the-art steam path design, matching diaphragms with reduced packing clearances, and newly designed inner casings made of erosion-resistant materials. This project challenged the imagination and capabilities of our industry. The stakes were extremely high. Vermont Yankee's continued existence in the highly competitive New England region power pool depended on the successful completion of the project, and General Electric's reputation as a major supplier in the retrofit turbine markets would be determined by this effort. Work began immediately and eventually involved manufacturing facilities from New York to South Korea. To ensure success, Vermont Yankee required commitment from the highest corporate levels. A project team was established representing the customer, GE field installation, manufacturing, engineering, and the piping contractor Fishback Power Services. This project team took ownership of all aspects of the project, including design, manufacturing, testing, factory assembly, shipping, installation, startup, and final acceptance testing. Although customer involvement in every facet of design and manufacture may appear to be a unique way for a supplier to do business, it has proved to be particularly successful at Vermont Yankee. The project team was empowered to reinvent the manufacturing process and provide direct feedback to final component design. The resulting improvements included the first fabrication of integral cover buckets, an inner casing completely fabricated of 1.25% chrome, and 12% chrome overlay in localized areas of erosion exposure. The challenge produced a number of creative solutions: additional inspection manways, rigging provisions for new expansion bellows, lift capability for the inner casing with diaphragms installed, borescope openings, flanged extraction joints, new moisture separator vanes and drain system, new coupling bolts, backup omega seals, a complete factory assembly. The list of design improvements goes on and on. At GE's Schenectady manufacturing facilities, factory assembly had not been accomplished in over 22 years. It required creative thinking because the bearings which form the basis for alignment remained in service at Vermont Yankee. The bearing centerline had to be artificially created at the factory to be able to generate the reference points from which all other dimensions and clearances would be established. Manufacturing, delivery, and installation schedules were developed, monitored, and adjusted continuously. The project team worked together daily, resolved problems jointly, inspected GE's manufacturing facilities weekly, had formal project meetings every month, and quarterly executive briefings. Inspection visits were made to suppliers in South Korea, Ohio, and New York to ensure quality requirements and schedule were well understood by everyone. Teamwork, empowerment, feedback, design improvement, cost control, and creative solutions were only part of a successful formula. World-class installation planning and execution were especially critical. In fact, outage planning and execution were the real success stories of the Vermont Yankee turbine retrofit project. Not only was outage planning carried to the devil's detail, but an attempt was made to anticipate potential problems and to develop contingency workarounds. For example, the single most important resource for project execution, the turbine building crane, was completely overhauled and upgraded immediately prior to the outage. Hour by hour crane usage studies over the entire outage period were used to distribute individual tasks and schedule crane preventive maintenance inspections. Additionally, a crane technical specialist was contracted on a full-time basis to supervise crane operation and assist in these inspections. Several potential problems were actually detected and corrected before they could affect crane availability. As a result, no crane problems affected project progress, and the successful crane operations contributed greatly to the overall success of the project. Other technical specialists were also contracted to ensure success. A peerless representative was on site during the moisture separator vane installation. Ovaco was present during coupling bolt disassembly. Tri-Tool was on site for all condenser pipe cutting, and shrink wrap was on site during the wrapping of the exhaust hoods. In all cases, the vendor technical specialists provided invaluable oversight and ensured the success of their unique tasks. Equally important was the planning to create a work environment that encouraged the craft personnel to work to their fullest capacity. Adequate scaffolding was prepared to access the difficult work areas inside the condensers. Hyperventilation, lighting, even a break area at the job site were made available. 5 major power distribution centers with multiple feeds were fabricated to accommodate the large number of welding machines that would eventually be operating simultaneously. Condenser cooling water would be intentionally operated for several days following plant shutdown to maintain a suitable work environment for the installation of tube protection, staging, lighting, and other services inside the main condensers. 2 barn doors had previously been cut into the condenser sidewalls to accommodate movement of personnel and equipment into this otherwise inaccessible area. Another critical part of the plan brought all project supervisors and craft foremen on site 1 month prior to the outage. This entire supervisory team trained, critiqued, and refined the overall plan, identifying and resolving concerns and establishing clear and focused goals. Craft personnel were also brought on site early for detailed task training in their specific assignments. Safety issues were included in this training. An aluminum horizontal joint deck plate was manufactured in segments to provide a safe and clean work surface and drop protection for those working below, inside the main condensers. Safety rails and cables provided further fall protection without hindering work progress. These actions, along with daily safety discussions, weekly safety meetings, and tangible safety incentive awards, contributed to the completion of over 82,000 hours of work without a lost time accident. In all, over 200 contract workers had been transformed into an integrated site installation team through pre-planning, team building, division of responsibilities, job site supervision, and empowerment. In the early morning hours of December 13th, 1994, the first shipment of components for the new low-pressure turbines began to make its way through the sleeping New England countryside. As has been the practice for 25 years of operation, Vermont Yankee would continue its business quietly and efficiently, with no disruption to the surrounding communities. A cold December morning would see the first of 35 deliveries by rail and truck that would set the stage for one of the most ambitious plant upgrades ever undertaken. Both original low-pressure turbines would be completely replaced with new rotors, inner casings, and diaphragms in a record time of 35 days. It was no accident that the first major components to arrive were the inner casing lower halves, even though they were the last components to be available for shipment. These were shipped first because they were to become the storage racks for the lower half diaphragms, as the diaphragms were received at the plant site. The lower half inner casings, complete with lower half diaphragms, would then be lifted as a single assembly onto the turbine floor as a full dress rehearsal for their eventual single lift into the condenser neck. It was all part of the plan. The shipping stands on which the new inner casings were transported were reused and became the interim storage stands for the new casings and the final storage stands for the old casings. Because the new low-pressure turbines are leased, another of the many creative solutions born of this project, they will permanently be stored on these shipping stands in outbuildings at Vermont Yankee to meet federal lease requirements. By February 1st, 1995, all new components and tooling had been received and staged on the turbine deck, 6 weeks prior to the start of the refueling outage. All new components were staged in their optimal positions as established by a three-dimensional scale drawing of the turbine floor. This showed the locations of both new and original components resting simultaneously on the turbine floor and represented the maximum floor loading during the outage. Both placement and floor loading had to be carefully examined from spatial, operational, and structural perspectives. Also completed at this time were permanent supervisor offices on the turbine floor, which allowed continuous supervision of work in progress and accommodated pre-shift briefings. With team motivation and morale at a peak, the entire project staff was given the day off 1 day before the outage began. On Saturday, March 18th, the plant shut down for refueling. At this time, all new components, spare parts materials, tooling, contractor training, access badging, shift assignments, planning, special HEPA ventilation, pipe cutters, welding machines, power supplies, condenser tube protection, staging, permits, detail planning, and contingency planning were ready to begin the installation phase. The installation phase began, as did every subsequent day during the outage, with a 6:30 a.m. briefing in the supervisor's office, attended by each foreman, work party leader, supervisor, and manager involved with the project. These daily briefings were a vital part of the plan. Objectives were reviewed, assignments made, progress reported, and challenges identified. If you were a part of the turbine project, you made sure to arrive at work early so you could review your objectives with your counterparts before the 6:30 briefing. While work was beginning inside the main condensers to measure and cut the 8 extraction pipes connected to each turbine casing, the outer exhaust hoods were removed, shrink-wrapped, and moved outside the turbine building for temporary storage. The shrink wrap was another creative idea which allowed these massive, slightly contaminated components to be moved outside the radiation control area, since there was no room on the crowded turbine floor for them. Clearance tagging was completed by 0800 on the morning of day 1. While bearing and coupling covers were removed, exhaust hoods were unbolted. By the end of day 2, the A exhaust hood and packing casing had been unbolted and removed and were being shrink-wrapped for outside storage. The shrink-wrap team had practiced and executed their skill perfectly. Both condensers had been opened and were approximately 50% staged. All 3 couplings had been disassembled, initial alignment readings taken, 2 stop valves disassembled, and disassembly of the 7 bypass valves was in progress. Day 4 saw both upper half inner casings unbolted and the A upper casing removed and in its storage location. Layout and cutting of the extraction piping was in progress inside both condensers. Cutting of the 16 extraction lines was to take place in 2 steps. The first and most critical cut was the lower finish cut, to which the new expansion bellows would be mated. This machine cut was located using a laser that could precisely identify a reference distance from the turbine center line that was exactly identical on all 8 extraction pipes. From this reference, all other measurements were made. The second cut was a flame cut just above the expansion bellows at the turbine snouts to allow lift clearance during the inner casing removal. At the same time, stop valve disassembly was completed by the valve crew. The centerline crew on the turbine deck continued with disassembly and removal of both upper half diaphragms. The success of the centerline work was matched by the condenser cutting crews, who completed their cutting operations slightly ahead of schedule. On day 7, both lower half inner casings and their lower half diaphragms were removed in a single lift. Because the original lower casing lift points were never designed to accommodate the combined weights of the inner casing and all diaphragms, special lifting brackets had been designed and fabricated for this lift. At 136 tons, this was the heaviest lift for our 140-ton turbine building crane. And it went flawlessly. Morale was at its highest, and the condenser cutting crew proudly autographed their accomplishment on one of the exhaust snouts. The work pace intentionally slowed somewhat as preparation for the installation began. The old expansion bellows and steam guides had to be removed from the condensers, along with extensive housekeeping and restaging of equipment. New steam guides, flanged expansion bellows, flanges, and Dutchmen were placed inside the condensers, neatly suspended out of harm's way. The Dutchman would be used to provide a light, easily moved mock-up of the actual expansion bellows, so mating flanges could be precisely positioned on the turbine snouts and extraction piping. They resulted in substantial time saving and eliminated risk to workers and equipment. The flange bellows were another unique innovation used to simplify alignment between the new turbine snouts and the existing extraction piping. The flanges also allowed welding to begin on the extraction piping without interfering with the centerline alignment. Of the 9th day, both new inner casing lower halves and their diaphragms were in place in both condensers and located to within 1/16 of an inch from their final locations. A long tight wire was used to transpose the bearing centerline to the inner casing and diaphragms. The traditional technology of using a tight wire was selected over laser alignment based on the uncertain effect on laser light of welding gases rising from the condensers and the confidence and experience of the centerline crew. On the 10th day, rough alignment had been achieved on both lower inner casings, and flange welding to the turbine snouts was allowed to begin. As each flange was tacked in place, the Dutchmen were moved to the next location, and the welding crew completed the fillet welding. The valve crew also completed their work on the stop valves and began to work on the control valves. Welding and post-weld heat treatment continued in the condensers, coincident with final inner casing alignment. Final alignment went very slowly due to the difficulty of moving 135 tons, a few thousandths of an inch in 3 dimensions. By day 13, final alignment was achieved, and welding of the 30-inch steam inlet pipes was allowed to begin. Each inlet pipe required 3 welds: a full penetration butt weld, and external and internal fillet welds where the pipe entered the inner casing. Rotor and bearing installation was completed for both turbines on day 18, 4 days ahead of the original schedule. Following rotor installation, coupling spacer measurements were taken and determined that the A casing, rotor, and diaphragms were so close to the original position that the original coupling spacer could be reused.